Machine Learning Fundamentals. Imagine you wanted to teach a computer to tell a cat from a dog. The old way was to write down rules: pointy ears, whiskers this long, tail like that. And it never quite worked, because the moment you wrote a rule, reality found an exception. Machine learning flips this completely. Instead of you writing the rules, you show the machine thousands of examples and let it figure out the rules on its own. In the next 20 minutes, you'll get the whole map of this field, what machine learning actually is, the 4 big families it splits into, the workhorse algorithms inside each one, and the handful of concepts that separate a model that works from one that quietly falls apart. No prior background needed. Let's get into it. What is machine learning and why do we need it? So let's define it cleanly. Machine learning is a way of building systems that learn, adjust, and improve from the data you feed them, without being explicitly programmed for every case. It's a branch of artificial intelligence. You can think of AI as the big goal, making machines act intelligently, and machine learning as one of the main ways we actually get there. Now, why bother? For simple tasks, you don't need any of this. If a job has a handful of clear steps, you just write the program and the computer follows it. No learning required. The trouble starts when the task is huge or messy. Think about recognizing faces in photos or predicting how a stock might move. There are simply too many possibilities to write a rule for each one. In those situations, it's smarter to hand the machine a pile of examples where some correct answers are already labeled and let it improve its own internal rule until it gets good at finding the right answer. That labeled pile is what we call training data, and it's the fuel for everything that follows. The 4 families of machine learning. Almost every machine learning method belongs to one of 4 families, and the difference comes down to one question. What kind of feedback does the system get while it learns? Family 1 is supervised learning. Here, every example comes with the correct answer attached, like flashcards with the answer on the back. Family 2 is unsupervised learning. No answers at all. The machine just gets data and is asked to find structure hiding inside it. Family 3 is semi-supervised learning, which sits in the middle. A small amount of labeled data plus a large amount of unlabeled data. And Family 4 is reinforcement learning, where the system learns by acting in an environment and collecting rewards and penalties, like learning a game by playing it over and over. Keep this map in your head, because everything else in this video is just a deeper look into these 4 boxes. Supervised learning. Let's open the first box. In supervised learning, you give the machine example inputs together with the answer you want for each one, and its job is to learn the general rule that maps inputs to outputs. The word supervised is literal. During training, the algorithm keeps guessing, and it gets corrected whenever it's wrong, again and again, until its accuracy is good enough. Once that rule is locked in, you can feed it brand new data it has never seen and get a prediction. That's the whole point. Learn from the past, then predict the future. Picture a spreadsheet where each row is one example. The input columns are called features, and the answer column is called the target. Supervised learning is just discovering the relationship between the features and the target, accurately enough that it still holds up on data that arrives tomorrow. Unsupervised learning. Now, the opposite case. In unsupervised learning, there are no answers. You only have the inputs, and you ask the machine to find the structure on its own. Since there's no target column, you can't make predictions in the usual sense, so the goal shifts. Instead of predicting an answer, you're trying to understand the data. Do the points naturally fall into distinct groups? Are some features secretly tied together? The most common version of this is clustering, where the algorithm sorts data into groups it discovers by itself without anyone telling it the groups in advance. A classic use is customer segmentation. Feed in shopping behavior and let the algorithm reveal which customers naturally belong together, so marketing can treat each group differently. Nobody defined those groups up front. The data defined them. Supervised versus unsupervised, side by side. Let's lock in the difference because this trips people up constantly. Supervised learning has a teacher. Every training example comes with the right answer. The algorithm learns a mapping function from inputs to outputs, and it gets corrected until it's accurate. The two big jobs here are regression and classification. Unsupervised learning has no teacher. There are no labels. The algorithm has to discover interesting structure by itself, and the two big jobs are clustering and association. And here's a subtle but important contrast. Classification and clustering both sort things into groups, but in classification, the groups are known ahead of time, and you're assigning new items to them. In clustering, the groups don't exist yet, and the algorithm has to invent them from the data. Same looking output, completely different problem. Regression. Time for the first real workhorse, regression. You use regression when the thing you're predicting is a number on a continuous scale. Sales figures, a car's mileage, a house price, next month's demand. The idea is to capture the mathematical relationship between a dependent variable, the thing you want to predict, and one or more independent variables that you already know. When there's just one input predicting one output, that's simple linear regression, and geometrically it's just fitting the best straight line through your scattered data points. We find that best line using a method called least squares, which is a fancy way of saying we pick the line that makes the total prediction error as small as possible. When you have many inputs at once, say you predict a store's sales from food sales, non-food sales, store size, and opening hours, that's multiple regression. Same idea, more dimensions. Beyond the basic versions, there's a whole toolbox: ridge regression, lasso, polynomial, nonlinear, each tuned for different data shapes, but they all share that one mission: draw the relationship, then use it to predict a number. Classification. Regression predicts a number. Classification predicts a category. That's the core split. If the answer is a label, spam or not spam, healthy or sick, truck or boat, you're doing classification. The algorithm, called a classifier, learns from labeled training examples and then sorts new, unseen items into the right class. There are two flavors worth naming. Binary classification has exactly two mutually exclusive options, like positive versus negative. Multi-class classification has three or more, like sorting an image into cat, plane, or car. And because the answers are categories rather than numbers, we judge these models differently. We don't measure average error, we measure things like accuracy, the fraction we got right, plus more careful scores like precision, recall, and the F1 score, all of which we'll touch on. The reason for the extra scores is simple. Raw accuracy can lie to you when one class is much rarer than the other, and these metrics catch that. The classification algorithms. Now, let's meet the algorithms that actually do classification, because each one has a very different personality. First, logistic regression. Despite the name, it's a classifier. It's the right tool when your answer is yes or no, and instead of predicting a raw number, it predicts a probability, then snaps that to a class. Next, naive Bayes. This one is built on probability and Bayes' theorem, and it makes one bold, naive assumption that every feature is independent of the others. That assumption is rarely perfectly true, but it makes the math fast and the results surprisingly good for things like spam filtering and sentiment analysis. Third, support vector machines. The idea here is beautifully geometric. The algorithm draws the boundary that separates two classes with the widest possible gap between them, and if the data can't be split by a straight line, a clever trick lets it bend into higher dimensions to find a clean separation. Fourth, k-nearest neighbors. This one is almost lazy. To classify a new point, it just looks at the handful of closest known points and takes a vote. Birds of a feather. And finally, random forest, which grows many decision trees and lets them vote, because a crowd of simple trees together beats any single tree alone. Neural networks and deep learning. Let's talk about the part everyone's heard of, neural networks. A neural network is loosely inspired by the brain. It's built from layers of little units called neurons. There's an input layer where data comes in, one or more hidden layers in the middle that do the heavy lifting, and an output layer that gives the answer. Each connection between neurons carries a weight, and each neuron has a threshold. If a neuron signal clears its threshold, it fires and passes information forward. If not, it stays quiet. The network learns by adjusting all those weights as it sees more training data, slowly getting more accurate. Now, deep learning is simply a neural network with many hidden layers stacked up, 3 or more, often far more. Why did this suddenly take off? Cheaper hardware and powerful GPUs made it practical to train these deep stacks. The payoff is that each layer learns progressively richer features, simple edges feeding into shapes, feeding into whole objects, which is exactly why deep learning now powers computer vision, speech recognition, language translation, and a lot more, sometimes matching or beating human experts. Inside unsupervised learning, clustering, association, dimensionality reduction. Back to the no labels world, because there's real depth here. Unsupervised learning does 3 main jobs. The first is clustering, grouping similar things together. The most famous method is k-means, where you pick a number of clusters, k, drop in centers, and assign each point to its nearest center, then keep nudging the centers and reassigning until nothing moves. There's also hierarchical clustering, which builds a tree of nested groups you can read like a family tree, mean shift, which slides points toward the densest regions, and the Gaussian mixture model, which softly says each point probably belongs to this cluster with some probability, rather than forcing a hard yes or no. The second job is association, finding rules like people who buy this also tend to buy that, the engine behind market basket analysis and product recommendations. And the third job is dimensionality reduction. When your data has too many features to handle, you compress it down to fewer dimensions while keeping its essential shape, which makes models faster and often more accurate. Semi-supervised and reinforcement learning. 2 families remain, and they round out the picture. Semi-supervised learning is the practical compromise. Labeling data by hand is slow and expensive, often needing experts. So you label a small slice, leave the rest unlabeled, and let the model use both. You get much of the accuracy of supervised learning for a fraction of the labeling effort, which is why it's so popular in the real world. Reinforcement learning is different in spirit. Here, an agent acts inside an environment with a goal, and it learns purely from consequences, rewards for good moves, penalties for bad ones. There are no input-output pairs handed to it. It has to balance exploring new strategies against exploiting what already works. This is the family behind game-playing AIs and robotic control, and it learns the way we often do, by trial and error. The concepts that make or break a model. Before we wrap, here are the make or break concepts that decide whether any of this actually works. First, how you split your data. You hold out part of it, a training set to build the model, a validation set to tune it, and a test set to check honest performance on data it never saw. If a model aces the training set but flops on the test set, that's the warning sign of overfitting. When data is scarce, cross-validation rotates which slice is held out, so every example gets used fairly. Second, signal versus noise. Signal is the real pattern you want. Noise is the random junk mixed in. Good models learn the signal and ignore the noise. Third, and most important, the bias-variance trade-off. A model that's too simple underfits. It misses the real pattern. That's high bias. A model that's too complex overfits. It memorizes the noise and breaks on new data. That's high variance. You can't fully minimize both at once, so the art of machine learning is finding the sweet spot in the middle. Complex enough to catch the pattern, simple enough to generalize. Summary. So here's the whole map in one breath. Machine learning lets systems learn rules from examples instead of being handed every rule. It splits into 4 families: supervised, unsupervised, semi-supervised, and reinforcement. Supervised learning predicts answers and breaks into regression for numbers and classification for categories, powered by tools like logistic regression, naive Bayes, support vector machines, k-nearest neighbors, random forests, and neural networks. Unsupervised learning finds hidden structure through clustering, association, and dimensionality reduction. And underneath it all sits one balancing act, keeping bias and variance low enough that your model works not just on the data you have, but on the data you'll meet tomorrow. If this gave you a clearer mental map of the field, the next videos go deep on each of these, one at a time. Thanks for watching, and I'll see you in the next one.